let's look at some more examples of common surfaces to parameterize. So one that we haven't talked about yet is a plane, and there are actually two good ways to parameterize planes. It kind of depends on the information that you start with. For one example, let's look at this plane. Let's parameterize the plane 2x plus 2y minus z equals 4. A plane like this is actually just a graph, right? We can think of this as the graph of a function if we just rearrange this equation a little bit. So write this as 2x plus 2y, move the z over there and the 4 to the left, 2x plus 2y minus 4 equals z. And so we could graph this plane just as the graph of a function. Okay, so that's not especially interesting. Let's look at a different example, because sometimes, right, this was so easy to figure out how to parameterize because we're explicitly given this plane with an equation, and we can turn an equation into a function. Z is a function of x and y. But that's not always how information about planes comes to us. So for example, let's parameterize the plane tangent to this helicoid at the point pi over 4, comma 3. Okay, so remember a helicoid is this sort of spiral shape. I'm only going to plot part of it like this. And we're at some point pi over 4, comma 3. And remember that if we hold v constant and change u, we get a helix going up the helicoid, right? And if we hold u constant and change v, what we get is a line going horizontally across the helicoid, right? And the tangent plane, well, both of these curves through this point, the one that we got from changing u and the one that we got from changing v, both of these curves should be tangent to our tangent plane. So in particular, if we could get a tangent vector along each of these curves, our tangent plane should contain both of those tangent vectors, right? So let's get a tangent vector in the u direction, right? Well, when in the past, when you've worked with parametric curves, you know that you could get a tangent vector just by taking the derivative with respect to your parameter, right? But since we have a parametric surface, well, we can get a parametric curve by holding one of these constant and taking the derivative with respect to the other parameter. That's just like a partial derivative, right? Since we have two inputs, we can take partial derivatives instead of regular derivatives. So partial r partial u, this will be the vector pointing along the curve we got by holding v constant and changing u. So I'll draw this vector here. This is going to be partial r partial u. Okay, so if we calculate that, we get, let's see, minus v sine u, v cosine u, and u. Sorry, 1, not u. Okay, now we should evaluate this at our point, right? Because this vector will point along the u curve, no matter for any point on the helicoid, but we're interested in this point. So we should evaluate this at pi over 4, comma 3. Okay, so sine of pi over 4 is root 2 over 2, so minus, so v is 3, and then sine of, so root 2 over 2. There we go. I got there eventually. For cosine, we get 3 root 2 over 2, and then 1. Okay, so this is the vector pointing in the u direction at this point. To get the vector pointing in the v direction, well, we should just take a partial with respect to v. So partial r partial v is going to be, let's see, cosine u, sine u, and 0. And again, we need to evaluate that at pi over 4, comma 3. And we get root 2 over 2, comma root 2 over 2, comma 0. Okay, so now we have these two vectors, and our plane is tangent to both of these vectors. So let's call this vector let me call this vector A, just so that I don't have to write out that partial derivative all the time. Let me call this one B. So let's write a new parametric curve. So it's a different R, so I should decorate this R somehow. Let me give it a hat, just so we remember it's not the same thing as the helicoid. So what should we do? Well, we need to start at this point, right? Our plane is going to be attached to this point. So we should start at the point we should start at the point on the helicoid where u is pi over 4 and v is 3. To figure out what point that is, we need to plug this into our parametric curve. So that's going to be, let's see, 3 root 2 over 2, comma, 3 root 2 over 2, comma, pi over 4. Okay. Now, since our plane contains both of these vectors, we should be able to add any multiple of either of these vectors and still be in the plane. Well, so how could we add any multiple of A? Well, we can add some multiple of A like this. What multiple? Well, it could be any multiple, and that's where our parameter is going to be. Right? Our parameter will be the scalar multiple of this direction A. And then, right, we need another parameter V and the vector B. All right. So this will parameterize the plane. To write this all out, it's going to be, let's see, 3 root 2 over 2 plus u times the u coordinate, the first coordinate of A, which is minus 3 root 2 over 2 plus v times the x coordinate to v, root 2 over 2. So there's the x coordinate, and then so on for the y and z coordinate. So let's plot all of this. Off screen, I've typed in all of the stuff that you get when you write out all of this and do all of the vector arithmetic. So for u, let's just go from minus 2 to 2 for both u and v, and let's plot the tangent plane in red just so that we can see it clearly against the background of the parametric, against the background of the plot for the helicoid, which is right here. So now we discover, have I made any typos? No. So there's our point. And you can see that if we look at the side view on this plane, it does appear to be tangent to the surface at that single point. Okay. So the point of this example is that in some contexts, the information you have about a plane is, you don't have an equation for it. Instead, you have two directions that are tangent to the plane. And if that is your situation, this is an especially nice way of parameterizing the plane, because you don't have to sort of detour through figuring out an equation for the plane. Okay, one more example of coming up with parameterizations for surfaces is if your surface is actually just a curve that has been rotated around some coordinate axis. Right? So if we have some function, say y equals f of x, we can parameterize this curve by saying it's, let's say u, if we have a parametric curve a of t, right, this is a of t. Well, for every point, to rotate this about a coordinate axis, for every point we just need to figure out a way to parameterize the circle about this coordinate axis that goes through that point, right? Well, this distance right here, this is one of your coordinate. This is one of your coordinate functions sitting inside of a of t. So maybe I should write a of t, a1, a2, a3, and remember that they're all functions of t. Okay, so this distance is going to be one of them. Let's say maybe it's a2. Okay. So what we need to do is make this go around a circle. How we do that depends on, actually, just to make things simple, let's assume that one of these is 0. Okay, let's assume that our curve lives in a plane and we're going to rotate it out of that plane. So to make this go into a circle, well, we need to, let's rotate about the x-axis. Okay. So this A2, this is going to serve as a radius, and we need to parameterize a circle that goes around in the YZ direction. Right? Well, to parameterize a circle in the YZ direction, we would need cosine and sine in our x and y coordinates. I'm putting cosine in the y coordinates so that when our angle is 0, we end up with A2. The radius of the circle is just given by A2, so we need A2 right here. The x coordinate just depends on, well, whatever this spot is. This is A of t right here. And let's use u instead of t for our parameter. So this is going to be A1 of u. This is A2 of u, and this is A2 of u. And then we need a new parameter to use as our angle that sends us around the circle in the YZ direction, so that will be v. Okay. So here is how we could rotate a curve about the x-axis if the curve starts in the xy plane. All right, so for an example, let's parameterize the rotation of this curve, this hyperbolic cosine graph, about the x-axis and also about the y-axis. So the curve that we're starting with here is t, comma, hyperbolic cosine of t, comma, 0. Okay, and we said to rotate about the x-axis, right, we're going to use hyperbolic cosine of t as if it were the radius of some circle, and the cosine and sine that generate our circle are going to be in the y and the z coordinates. So, right, like this. We're going to use v for the parameter that sends us around the circle. We're using hyperbolic cosine of u as our radius for this circle. And then in the x-coordinate is just the x-coordinate of this parametric curve, which is t, but remember we're switching to u. So here is the rotation of this hyperbolic cosine graph about the x-axis. Well, now let's rotate it about the y-axis. Y-axis. Okay, well, now we're going to have our cosine and sine in the x and the z direction, like this. And what we're using as the radius this time is the x-coordinate of our parametric curve, so that should be, I said I was going to use u instead of t. So let's put a u here and here. In the y-coordinate, we need hyperbolic cosine of the parameter u that takes us along the graph of the curve. And then again, v is going to be the parameter that sends us around a circle. So here's the parameterization of rotating this graph about the y-axis. So before we graph these, let me just remind you what the graph of hyperbolic cosine looks like. It looks something like this. It sort of looks vaguely exponential on either side, and in the middle it looks very flat. Okay, so let's graph these two surfaces. Let me comment out all of this stuff. Okay, so here's the one about the x-axis. Okay. You can see the graph of the hyperbolic cosine graph right here. Right there it is. And the x-axis is going sort of through the middle of this thing. So if you take this curve that you see on top and rotate it about the axis going through the middle, you do indeed generate this shape. I don't know what to call this shape. A spool, like a spool of thread, I guess, would be one way to describe this. Okay? So if we instead take this same graph, this one here, and rotate it about the y-axis, So the y-axis is, roughly speaking, going up and down in this picture. So if we take this and rotate it about the y-axis, we get a very different looking shape, which is no surprise. I mean, if you rotate around a different direction, in general, you will get a very different shape. We get this bowl shape. So again, if we look at it from above, you can see the hyperbolic cosine graph right there. It might look like it's a parabola, but if we looked at more of the graph, it would not seem so parabolic. We get this bowl shape instead of a spool shape, right? So if you rotate this hyperbolic graph around a vertical axis, we get this bowl.